All right, it's your old pal, Mr. Cook, and we're getting started on the back page of the group work. We just did the first page and kicked the crap out of it, so now it's time to work on the back page here. So if we're trying to determine if a binomial is a factor of a polynomial, we just do something very similar to what we did on number 3, and that's use the synthetic division algorithm and check to see if the remainder is equal to 0. If it is equal to 0, then that means that it is a factor. If it is not equal to 0, then that means it is not a factor. Pretty simple process. You started off by finding out what value you're supposed to put in the corner for the synthetic division algorithm, and to do that, you set your potential factor equal to 0 and solve for x. So if I have 2x plus 1 equals 0, if I solve for x, I subtract 1 and then divide by 2, so that means that x will be equal to negative 1/2. So that negative 1/2 is the number that's going to go in the corner over here. So now we test this with the synthetic division algorithm for these coefficients. So 6x to the third, 41x squared, negative 9x, and negative 14. Since negative 14 is the constant number, we put a little box underneath it, and that's where our remainder is going to go. So we need to check and see if it's equal to 0. All right, so negative 1/2 times 6 is negative 3. 41 minus 3 is 38. 38 times negative 1/2 is a positive 19. Negative 19. Negative 19 times plus negative 9 is a negative 28. Negative 28 times negative 1/2 is positive 14. 14 minus 14 is 0. So that means that since the remainder is 0, then that means that yes, indeed, 2x plus 1 is a factor of this polynomial. So in other words, since it's a factor, we should be able to factor out the expression 2x plus 1 from this, and then we'd have a whole bunch of other stuff left over that we try to factor a little bit further. But that just kind of tells us whether or not it does factor from the get-go. All right, next. If x plus 3 equals 0, if we subtract 3 from both sides, x is equal to negative 3, so negative 3 is the number that goes in the corner. And we use the same numbers as before, 6x to the third, 41x squared, negative 9x, and then negative 14 as our constant value. So again, we write the little box underneath the constant, and we check to see if it works with the synthetic division algorithm. 6 times negative 3 is negative 18. 41 minus 18 is 23. 23 times negative 3 is negative 69. Negative 69 plus negative 9 is negative 78. Negative 78 times negative 3 is a positive 234. 234 minus 14 is 220. Is that equal to 0? No, it's not, so that means that this is not a factor of the polynomial. All right, so simple enough. That's just the factor theorem, and we move on from there. So number 5 is kind of testing out a ton of stuff at once. We have to list the potential zeros, so that's the rational roots test, and we're going to do that for 2 different functions. We're going to find all the rational zeros that we can, and that's going to be our calculator along with these things right over here. And then also we're going to find the remaining zeros. So if there's any imaginary or irrational zeros, we'll find those through whittling this down to a quadratic and then using quadratic formula or some other method to solve. So let's start with listing the potential zeros. So to do that, we take the constant value and the lead coefficient, which in this case is 1, and we put the constant over the lead coefficient, list off all the factors of each. So we have 9 is a factor of 9, 3 is a factor of 9, and 1 is a factor of 9. And then the only factors of 1 is 1. So now we just make combinations of the fractions that are formed. So 9 over 1, so that's 9. 3 over 1, that's 3, and 1 over 1, that's 1. And then just remember to put a plus or minus in front of each of these because, potential zeros, you could have 9 that could get plugged in here and get 0, or negative 9, or 3, or negative 3, or 1, or negative 1. And we'll test that out in a second. So similarly for the g function, then we use the constant value and the lead coefficient, so 7 and 2 respectively. We put the constant value on top, the lead coefficient in the bottom. We list off the factors, so 7 has factors of 1 and 7 because it's a prime number. Same thing with 2, so that's 1 and 2. Now we list off the potential fractions that we get, so 1 over 1 would give us 1, 7 over 1 would give us 7, 1 over 2 would give us 1/2, 7 over 2 is 7/2, and then we just put plus or minus in front of each of those for the same reason as the previous one that we just did, because it could be a positive or a negative answer for either of those. Okay, now let's actually find the rational zeros, and to do that we're going to cheat a little bit and use our calculators. Okay, so let's graph this thing out. So y equals x to the fourth power plus 6x to the third power plus 10x squared, and then plus 6x, and then minus 9. Oops, plus 9. Plus 9, there we go. Then hit graph. And here's our graph. Lovely. Okay, so it looks like for one of our zeros, in other words, the x-intercept, we're going to have -3. Let's verify that by going to the table. So we hit second and then graph, and it brings up the table. And sure enough, -3, 0 is an x-intercept. So that means that -3 should work with our synthetic division algorithm. And in fact, we are just overcome with good luck here because it looks like at -3, it deflects backwards. So if you go back to your, this problem over here, whenever we have, an x-intercept that goes back on itself, that means that the multiplicity is going to be even. So that means, in other words, that if the multiplicity is even, because this bounces off like this, then -3 will work twice with the synthetic division algorithm. So check it out. If I'm going to use -3 in the corner for synthetic division with this polynomial, so 1x to the fourth, 6x to the third, 10x squared, 6x, and 9. We should get 0 for our remainder. Let's check that out. So 1 times -3, and then -9, and then -3, and then -9 again. Yep, sure enough, it works. And since the graph at that x-intercept bounces off of the axis, -3 should work a second time. So check it out. -3 gets plugged in for synthetic division. Our constant should be 0. Let's see if that's the case. 1 times -3, that gives me 0. That's 0. That's 1. And -3, yeah, sure enough, it works out. So this gives us our 2 rational zeros. So far our 2 zeros that we have are -3 and -3. So in other words, -3 with a multiplicity of 2. That's what we have so far. Now let's find our remaining zeros. I stopped short of getting more rational zeros from this because the quadratic that we get from it, here, let me get rid of that little arrow. Just remember that to write out the polynomial that you get as a result when you do synthetic division, the first number outside of the remainder is going to be your constant, and then this is the coefficient on your x value, and this is the coefficient on your x squared. So that means that we have the following polynomial as a result. X to the second power, so 1x squared, plus 0x, so we can just leave that out, and then plus 1. This doesn't factor because we can't think of any numbers that multiply together to be 1 and add together to be 0. And this isn't a nice little difference of squares like this one where we can factor it out real nicely because it's not a minus in between there, it's a plus. So this is only going to give us imaginary solutions, and that's why they're called the remaining zeros, not the rational zeros. So to find those missing zeros, we take x squared plus 1. And this is a special case. Since it's a sum of squares, we just set it equal to 0 and solve. So we can subtract 1 from both sides. That's x squared is equal to -1. And then take the square root of both sides. So we get x is equal to plus or minus the square root of -1, which is also saying, plus or minus I. So those are our other 2 zeros that we get. So we have -3, -3, and then also plus or minus I. So I and -I. And those are the 4 zeros that we're going to have. And remember that you can always tell the number of zeros that you're going to have in total, counting multiplicities, by just looking at the degree of the polynomial. And since it's 4 in this case, we should have 4 zeros, which we do. So all 4 of them are here, 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 and here. Okay, let's do the same thing. So same treatment with this polynomial. All right, so we graph it out with our calculators. All right, so let's see, y equals, and then we clear it out, 2x to the third power minus 5x to the second power plus 11x plus 7. Graph it out. And there's our graph. Okay, so that kind of sucks. We only have an x-intercept in between 0 and -1. Well, there's no values that just stick out that we can use for synthetic division. So what we're going to do is go back over to our rational roots that we had. And out of these 8 numbers that we have selected as possible rational roots, only one of them is between 0 and -1. The only one that's between 0 and -1 is -1/2. So we're going to try -1/2 with synthetic division. So we do -1/2 in the corner. And then we get 2x to the third, -5x squared, 11x, and 7. So underneath the 7, we're going to put our remainder box, and let's see if we get 0. So 2 times negative a half is negative 1. Negative 5 and negative 1 makes negative 6. Negative 6 times negative a half is 3. 11 and 3 makes 14. And then 14 times negative a half is a negative 7. And sure enough, we get 0 there. All right, so this means that if we wanted to factor this out, we'd have the following factor. So negative 1/2 gives us a positive 2x plus 1. And since we have this lead coefficient of 2, that means we need to divide these coefficients by 2. The reason that we're doing that is because technically we're checking this factor as x minus a negative 1/2. So in other words, x plus 1/2. So to turn it into a factor with integer coefficients, we needed to multiply this by 2. And to keep everything even or equal, if we multiply this by 2, we have to divide something else by 2. And that's what we're going to do over here to keep it simple. So we end up with 1, negative 3, and positive 7. So that gives us the quadratic x squared minus 3x plus 7. And there's no integer values that multiply together to be 7, add together to be negative 3. So this is, again, a factor that will not, it's a quadratic that will not factor. So we need to use an alternative method. We can't use the square root method like we did here because it's not a sum of squares or a difference of squares. So we're going to use quadratic formula instead. So for quadratic formula, our a value is equal to 1, our b value is equal to negative 3, and our c value is equal to 7. So, plug it into the formula. So we have negative b, so negative 3, and then plus or minus, and then it's going to be the square root of b squared, so negative 3 squared, minus 4 times a, which is 1, times c, which is 7, all over 2 times a, and a again is 1. So to simplify this a little bit more, a negative of a negative is is positive, so 3 plus or minus, and then this is 9 minus 28. 9 minus 28 is negative 19. And then 2 times 1 is 2. So the only thing we can really do to simplify this a little bit is to move that negative out to the front. So it becomes an I. So we have 3 plus or minus I times the square root of 19 over 2. So these are our remaining zeros. So we're supposed to have 3 of them because the degree is 3. We have one of them at negative 1/2, and then the other 2 are 3 plus I squared root of 19 over 2 and 3 minus I squared root of 19 over 2. All right, so that concludes our zeros, and I'm going to stop the video here before we move on to the next ones. So that's it for zeros. Make sure you ask questions if you have any about this stuff. Ask your teacher or send an email or whatever.